Topic of conversation is zeros of polynomial functions. So the fundamental theorem of algebra says that if f of x is a polynomial of degree n, provided n is greater than 0 and f has at least one 0 in the complex number system. So remember our numbers, we have our natural numbers, like our counting numbers that we learned when we were little, and then we realized that there was 0 as well, and then integers, positive and negative, so we learned about the negative counting numbers. Our rational numbers include our fractions and decimals. Then we learned about numbers like pi and e, which are irrational numbers, along with the square root of 2 and so forth. And then we have, those are all part of the real number system. And finally, we have our complex number system that encompasses real numbers plus imaginary numbers. So the fundamental theorem of algebra says that if we have a polynomial of degree n, you have at least one 0 in the complex number system. So our linear factorization theorem says that if we have a polynomial of degree n, then f of x has to have n zeros and n factors. So whatever the degree of the function is, or the polynomial function is, that will be the number of zeros and the number of factors. However, not all of them will be unique. Remember that we can deal with multiplicity. So you could have the same repeated 0 multiple times. So our linear factorization theorem says that if we have zeros of 2, -1, 4i, and -4i, and we are to write the linear factors of f of x, that means that f of x will be a product of x minus 2, x plus 1, x minus 4i, and x plus 4i. So these are the zeros, these are the factors. If we multiply the factors together, we get our polynomial. If we find our zeros, we're back to where we started. The rational zero test says that if you're trying to figure out what possible rational zeros you can have in a polynomial, then we have a polynomial of a sub n to the x times x to the n plus another constant times, or plus another number times x to the n minus 1 and so forth. Provided these are all integer coefficients, then every rational zero has to be of the form p over q, where p are factors of the constant and q is factors of the leading coefficient. Okay, so if we're trying to figure out what the possible rational zeros of f of x equals x cubed minus 7x minus 6 are, then we would say, hey, if my factors of my constant over my factors of my leading coefficient are the only possible rational zeros, fractions, decimals, integers, then we're working with plus or minus 6, plus or minus 3, plus or minus 2, and plus or minus 1 over plus or minus 1. Because 6 has factors of 6, 3, 2, or 1, both positive and negative, and the leading coefficient 1 has factors of 1. So of all the possible numbers in the world that could be zeros of this polynomial function, there are only 8. And this is our potential pool of zeros. So to find the rational zeros of 3x cubed minus 20x squared plus 23x plus 10, instead of just randomly choosing random numbers, we can actually choose numbers like factors of 10 over factors of 3. So factors of 10 are plus or minus 10, plus or minus 5, plus or minus 2, and plus or minus 1, and factors of 3 are plus or minus 3 and plus or minus 1. So all of our possible factors are 10/3, 10, 5/3, 5, 2/3, 1, 2, and 1/3, and 1, positive or negative of each. And we know by our remainder theorem that if we synthetically divide by any of these factors and we get a remainder of 0, that is a 0 of this function. So we're going to bring our leading coefficient, or all of our coefficients down. 3x squared minus 20x, 3x cubed minus 20x squared plus 23x plus 10, and we're going to try some possible zeros that we could have here. So most of the time students try 1 or -1. So let's try +1 and see what happens. We bring our 3 down. 3 times 1 is 3, -17 when we add. -17, 23, and -17 is 6. 6 times 1 is 6, and that does not get us a 0. So we could try instead to try a -1. Our 3 comes down, and -1 times 3 is a -3, -20, and a -3 is a -23. -1 times -23 is 23. 23 and 23 is 46, and that is definitely not going to get us a 0. So -1 didn't work. So maybe 2. 3 comes down. 3 times 2 is 6. 6 and -20 gets us a -14. 2 times -14 is a -28. 23 and -28 is a -5. 2 times -5 is a -10, and lo and behold, -10 and 10 gets us a 0. So we have found one of the rational zeros. We know that 2 is a 0, and x minus 2 is a factor. Our fundamental theorem of algebra says that we need to find 2 others. There are 3. This was a cubic, so we've now depressed it. It's now a quadratic. 3x squared minus 14x minus 5. So if there are going to be any other rational zeros, this has to be able to be factored. If we're going to factor it, we're going to either try guess and check, in which we say, hey, what are the factors of 3x squared, 3x and x, and what are the factors of 5? Well, the only factors of -5 that will subtract when we multiply this 3 in here to a -14 has to be a 5 and a 1. If I put the 5 in the first spot, that would possibly get me 8 or 2. But if I put the 5 in the second spot and the 1 over here, 3 times 5 is 15. We want that to be negative. And 1 times x is 1. So if I FOIL that out again, I'm sure to verify 3 times x, or 3x times x is 3x squared. 3x times a -5 is a -15x. Positive 1 times x is positive x, and 1 times a -5 is a -5. These two do add up to a -14x. So 3x squared minus 14x minus 5 has 2 other zeros. They are a positive 5. If x minus 5 equals 0, x has to be 5. And if 3x plus 1 equals 0, then 3x is a -1, and so x is a -1/3. And our other factors were 3x plus 1 and x minus 5. All right, conjugate pairs. Well, conjugate zeros, or complex zeros, travel in pairs. They have to travel together. If they didn't, we would have i's all over the place, and it wouldn't have integer coefficients. So we're going to let f of x be a polynomial of the function, a polynomial function that has real coefficients, no i's in there. If a plus bi, where b is not equal to 0, is a 0 of the function, then the conjugate pair a minus bi also has to be a 0 of that function. So to find a 4th degree polynomial with 0, 1, and I as its zeros, if 0, 1, and I are zeros, then that means negative I also has to be a 0. Because if I multiply x minus I, the factor of positive I, by x plus I, the factor of negative I. When I distribute this out, I get an x squared plus xi and minus xi, which cancels, and then a minus I squared. But we know an I squared is a -1, so a negative 1 is a positive 1. So this piece is x squared plus 1. I have to take it times the x minus 1, and eventually times an x. So when I multiply this out, I get an x cubed, a minus x squared, a plus x, and a minus 1, all times x, or an x to the fourth minus x cubed plus x squared minus x. That's a fourth degree polynomial with those zeros. To find all the zeros of f of x equals x to the fourth minus 4x cubed plus 12x squared plus 4x minus 13, given that 2 plus 3i is a 0, means that we also have 2 minus 3i as a 0. So one way to approach this is to find the factor of 2 plus 3i, which would be x minus 2 minus 3i, and the factor of 2 minus 3i, which is x minus 2 plus 3i. If I multiply those two out, I can use product boxes to help keep things organized. And x times x is x squared, x times a -2 is a -2x, x times a -3i is a -3xi, -2 times x is a -2x, -2 times a -2 is a +4, and -2 times a -3i is a +6i. X times 3i is 3xi. -2 times 3i is a -6i, and a 3i times a -3i is a -9i squared, but I squared is a -1, so this will be a +9. Combining our terms, we end up with an x squared minus 4x. The i's should disappear if we've done this right, and 4 and 9 is 13. So we have a quartic power of 4, degree of 4, and we can divide this out by our quadratic that we found by using our two factors that had the complex zeros. And long division, x to the fourth minus 4x cubed plus 12x squared plus 4x minus 13 being divided by the quadratic x squared minus 4x plus 13. We ask ourselves how many times is x squared going to x to the fourth, and it's x squared times. We multiply it out. X squared times x squared is x to the fourth. X squared times a -4x is a -4x cubed. And x squared times 13 is a 13x squared. Change the signs of everyone and add. X to the fourths are gone, the x cubes are gone, and we'll have a -13x squared plus 4x minus 13 when we bring our remaining terms down, and x squared has to be multiplied by a -1, not 13, -1 to get an x squared. So x squared times a -1x is a -1x squared. -4x times a -1 is a positive 4x, and a positive 13 times a -1 is a -13. If we now change all of our signs, we get a remainder of 0. So we know that we have factored that or multiplied it out properly. So if these are two of our factors, the other factor is x squared minus 1, which factors into x minus 1, x plus 1, difference of squares. So if 2 plus 3i is a 0, 2 minus 3i is a 0, positive 1 is a 0, and -1 is a 0.